Hopefully I have 2 feet on the ground. I'd like to thank the organizers for inviting me here. I was a student here 29 years ago, and I have fond memories of the place. And so in the spirit of the talks 29 years ago, I'm going to do a chalkboard talk for you. Since it's getting a little bit late and my stomach is telling me that it'll be time to finish soon, this will help slow me down and bring it to a natural close, I think. Although I'm going to show a computer simulation at the end, hopefully. So I want to tell you about a collection of methods that we've coined direct statistical simulation to counterpose it against direct numerical simulation. It's basically a set of tools to directly get at the statistics of, say, geophysical fluid dynamic systems, maybe astrophysical systems, even low-dimensional chaotic systems. And so there are many possible avenues to explore. I'm going to just illustrate one concrete example in the second half of the talk. And you can see, you can read about this in some detail in this review article that we wrote that's going to be appearing in a book someday. It's waiting for the other co-authors to finish their chapters. Okay, so all right, so I should begin with, well, what's the purpose of this? What's the purpose of direct statistical simulation? So there's really, I think, two purposes. One is to gain a better understanding. And so this was emphasized by Lorenz when he noted back in '67 that weather simulations already at that point, numerical weather simulations were already beginning to look a lot like weather. And so then it sort of leads to a philosophical question of what's the purpose behind such simulations, apart from the practical need to predict the weather. Can we look at the forest from the trees? How are we going to see the key features, the key dynamical features? And so he suggested that solving for the statistics might be a way to clarify things, and that's kind of the approach that, or our inspiration, our initial inspiration. But there's a second possibility, which is that there could be some practical gains to be had. For example, we might hope to construct new subgrid scale models to deal with statistically the unresolved physics perhaps in a climate simulation. And maybe we could do this in a more systematic way, in a more physically based way, reduce the number of parameterizations that we have to tune in order to achieve this goal. Or we might be interested in, for example, accessing rare events. And I think Freddie spoke about this last week, I believe. So we might have heat waves, for instance, some extreme events in the climate system that are difficult to access by direct numerical simulation because you have to simulate for many years of model time. And so if tools could be developed to hone in on these events of interest, that could be of great practical use. I'm not going to talk about that approach today, but that's certainly, I would say, that falls under this kind of general scheme. So when we talk about statistics, we should ask the question, what statistics? Especially when we're looking at a high-dimensional system, there are many different statistical questions that we could ask. And so an example of this would be maybe a single point PDF. So by point, I mean that we have a high-dimensional field. Say we could label it with some vector here, where that vector might be n-dimensional. And we want some distribution of that field at a single but not a joint distribution, just that one field. And so that's already a very challenging object to look at, as Henk discussed this morning. We might be interested in low-order moments, and that's going to be the example that I will focus on later in a moment. So this be means and variances, perhaps. Then we could also ask questions about autocorrelations. So perhaps these low-order moments are equal time. So we might look at a correlation between some field and another field, temperature, velocity at the same time. Well, we might also be interested in how these correlations evolve in time. So autocorrelations, and then extreme events, large deviations. So this isn't certainly an exhaustive list, but it's some flavor for what we might be interested in. Yeah. Okay, I will explain that in more detail. So that's the case I'll go into in some detail. Okay, so if we're looking at statistics, we also have to discuss what type of averaging we want to perform, what averages. And here again, there are many choices. So we heard about today in Ted's talk about zonal averaging. And that's going to be the case that I'll focus on. But we could have ensemble averaging, or time averaging, or perhaps some more exotic forms of averaging. So a lot of choices there too. And which choice we make, of course, depends on the kind of questions that we're interested in. Models, so many different types of models. Fundamentally, we should make a choice between deterministic and stochastic. And we saw that quote by Lorenz earlier, that the choice of this is basically based on convenience, depending on what degrees of freedom you want to hide, perhaps not treat explicitly, maybe treat as a stochastic variable, which ones you want to treat explicitly. Usually I like working with deterministic models, but the example that I'll show you shortly is going to be a stochastic one, because not because it has any fundamental truths to it, but it's a very useful kind of toy model. And then things are interesting because of nonlinearities. And it sounds like there'll be quite a bit of discussion about this this week. But the fundamental one I'll be looking at today is just the advective nonlinearity. So it's a kind of quadratic nonlinearity. But there are many other possible nonlinearities. For example, we could have latent heat release, which would be not quadratic. You have some temperature drops, and you have a condensate and sudden release of heat. So that would be more like a step function nonlinearity. And how to deal with those, I think within this framework, is one of the big open questions that we're faced with. So let me adopt this quadratic nonlinearity and just write a kind of general dynamical system that represents the sort of problem that I'm interested in. And so we have some equation, some tendency, and we'll see a more physical example of this in just a moment. This might be forced. And then there could be some linear term that perhaps includes some dissipation by friction or viscosity, and a quadratic interaction involving two powers of the field variables, and then perhaps some stochastic forcing, which I'll write in a kind of physicist way instead of using the terminology that was introduced earlier in the morning, but it's basically equivalent. So this is some random variable, and which has some statistical properties. So we might like to write this down in terms of some discrete degrees of freedom. We could imagine, for example, working in Fourier space or some space where we, on a lattice, where we have a bunch of modes that we can label with an index I. And so just to be concrete, we could write this linear operator, for example, as Lij times Qj, and there's implied summation over a repeated index. So the sum would go over n degrees of freedom. And then similarly, Qijk, Qj, Qk, plus eta I of t. Okay, so that already encompasses quite a few interesting geophysical models, basically dry flows, both barotropic and baroclinic models. But since Ted is focusing on barotropic physics this week, I thought I'll also stick to a barotropic model. And so the concrete example I want to look at is one that's already been mentioned a little bit, which is the evolution of vorticity on a rotating sphere and then subjected to some random forcing. So I'll introduce the vorticity. This is the vertical component of the curl of the velocity field. And although maybe I should have given this lecture in a few days' time when Ted has introduced this equation, I'm sure that many of you have seen it. So let me write it down, and then I'll ask you to see how many of you have seen this before. So this says that the tendency of this vorticity field, which lives on the surface of a sphere or on a beta plane, is equal to the Jacobian of the vorticity plus the Coriolis parameter and the stream function. So that's our quadratic nonlinearity. And then we would have some linear damping and perhaps some forcing, but I won't choose any deterministic forcing. I'll just have some stochastic forcing, some source of energy for this problem. And so here the stream function is related to the vorticity by taking the Laplacian of it. And the Jacobian can be written in a coordinate independent way by looking at the cross product of the gradients of A and B. So the gradient of A crossed into the gradient of B, and we take the vertical component of that. How many of you have seen this sort of equation before? Great, okay. So, all right, so this is basically, the start of geophysical fluid dynamics. And let me be a little bit more precise about this linear damping that I'm going to choose. So let's have some Rayleigh friction, which is going to slow down the flow. And then we're going to include some hyperviscosity to get rid of the any entropy that cascades down to small scales. So and then I guess I should say our Coriolis parameter on the sphere is 2 times the rotation rate of the planet times the sine of the latitude. So actually this very model is discussed on a poster just outside the door by Laura Cope. And so I encourage you to go talk to her about this model if you want to discuss maybe some of the physical justification for it. I'm happy to say something about it if you're interested. We'll see a simulation of it in just a moment. So, okay. So we have this equation of motion, and this is, of course, our Jacobian operator here. Although there's also the F term, which is just a constant. So actually, a piece of this Jacobian is really a linear operator, so we should really group that over here, right? So this linear operator isn't quite complete. There's a little bit of linear over here that needs to go over there. So what are these low order moments that I want to investigate? Well, I want to look at the vorticity well, conveniently I've used the symbol Q just as a general dynamical variable, but it could also be the absolute vorticity, which is the relative vorticity plus the planetary vorticity F. What I'd like to do is to look at the moments of this Q. So perhaps Q bar, and let me take a zonal average. So let's choose a zonal average. So 1 over 2 pi integral over the longitude of Q of phi and lambda d lambda. So that's the zonal mean. That's the thing that we've already seen some plots of, even though, of course, the Earth doesn't have perfect azimuthal symmetry. It still could be a useful quantity to look at. And if we're looking at idealized models like this one, then it's a natural average to consider, since the model itself has that symmetry, rotation around the axis. But we may not only be interested in the mean, we might want to know something about the variances. So first of all, actually, I should emphasize, of course, this mean is in general going to depend on the latitude. So we've had a kind of dimensional reduction from a two-dimensional object to this one-dimensional object by doing this mean. But we might also want to look at Q at phi 1 and lambda 1, and Q of phi 2 and lambda 2, and do a zonal average of those. Yeah. Q is also a function of time. So it could be that this zonal mean depends on time, and I haven't explicitly written that. Yeah, we'll have time-dependent equations that will show that shortly. Yep. Yeah. These are all numerical experiments you could do. I'm going to show you this one, but we could change it to the fourth if you want. It won't matter much for this model, yeah. But it could be, these kinds of questions, these detailed questions might be important to investigate if you're, writing a publication or something. So, yeah. We don't. So I don't have ordinary viscosity because, well, we could have ordinary viscosity, but I choose not to here because that tends to be too much damping. So, and I'm segregating all the damping over here of energy removal. So this isn't really removing energy. Any other questions? All right, so this thing is the second moment. Now, I guess we could call it M2. And it's a function of 3 variables, phi 1, phi 2, and the difference of lambda 1 minus lambda 2. Because of the zonal symmetry of our problem, then as long as the flow is ergodic and sort of exploring phase space, then it shouldn't matter whether I have this choice of the 2 lambdas, or if I shift them all by both of them by 10 degrees. It should matter only on the difference between the longitude of those 2 points. So we've gotten some reduction in our dimensionality, although this is already kind of an expensive object because our underlying field is 2-dimensional, now we're 3-dimensional. So the traditional approach for getting these statistics would be to do a lengthy time integration through your direct numerical simulation. You would accumulate statistics over time and then compute time averages and then maybe zonal averages. Or you could do a zonal average and then look at its evolution as a function of time, but I would like to try to directly solve for these statistics. All right, so how are we going to do that? Well, let's just try something rather naive. Let's go to our equation of motion and see if we can average that equation of motion, and what will that bring us. So if I do a zonal average on this equation, for instance, I'll write that Q dot zonal average is equal to F. We'll assume that F is already zonally symmetric. Our model is zonally symmetric, plus L of Q, and I'll zonally average that, and then Q of QQ, and the zonal average of the stochastic forcing. Yep.
So we basically assumed homogeneity in the zonal.
Yes. Yeah.
Could you tell us again what the justification?
Well, as long as there's not some structure that just sticks, that just persists at one latitude, everything is sort of sweeping around, then the zonal average, or if we look at, say, a time average, that structure, that thing should only depend on the difference between these two quantities. But you might worry that, like in the case of Jupiter, where you have this red spot that's hanging out there for hundreds of years, maybe that is bringing into question this assumption, and in which case you might want to choose a different averaging operation like ensemble averaging. So that's something that Navid has investigated quite a bit, and you could talk to him about that ensemble averaging. Okay, any other questions? Well, so let's assume that our stochastic forcing doesn't have any zonal mean contribution. So that'll go away. And because this is a linear operator, we can actually interchange the order of taking that average for most averages. There's some, you have to be a little bit careful about this. If you have a linear operator, maybe that also, if you have a vertical structure and you're taking vertical averages, and you might question that. But for the model that we're looking at, this is fine. The big problem here, of course, is this guy, which schematically we have an average of these two Qs, and they're really at different locations because this involves some differential operators. So it needs to know about how the field varies from point to point. So we need this object, R1, R2, equal time, at least, but at different spatial locations. And so this is the famous closure problem, because if we have a linear model, we just have means appearing on both sides of this equation. But as soon as we have this quadratic nonlinearity, then we have this new object that we have to specify in order to solve for this mean. So what do? Well, we can go back to our equation of motion and multiply it by Q. So Q times Q dot, and then average it. And so that's actually going to be 1/2 times the time derivative of this object. All right, so that will give us the tendency for this object. So if we can evolve this forward in time, then we can feed it into our equation here. Using our equation of motion here, that would be F times Q bar, and then we have plus Q times L of Q, average. But that's okay because we have here 2 Qs, but we also have 2 Qs over here, so it's closed. But of course, I think you can see what the problem is going to be. Again, when we have our quadratic term here and we average it, that now we have to have information about a third moment. And so it's turtles all the way down. We just keep on going with this process. And it's getting pretty bad because the dimensionality of these objects is increasing. When we have a third moment, that's going to have, even after zonal averaging, 5 degrees of freedom. So we want to terminate this as quickly as possible. And the way that we're going to terminate this is by a closure which assumes that the third cumulant, yep, just a second, is equal to 0. All right, I'll define that in just a moment. Was there another question? Yeah. So there's also the eta term, and let me come back to that. So what we can do is basically is a short time average, and then in the second equation, the covariance of the noise will appear if we have white Gaussian noise. Yeah. Okay, so what is a cumulant? So a cumulant, at least up to the third cumulant, is equivalent to a centered moment. So what we should do is define Q, our field, as a function of theta and phi. Sorry, I've switched coordinate systems. Phi and lambda to be Q bar, which only depends on phi, plus some fluctuation, Q prime of phi and lambda. And now what we can do is look at that second cumulant again, or the second moment. So if we compute the zonal average of Q of R1, R2, and substitute in here, then this is going to be equal to Q bar at phi 1, Q bar at phi 2, plus Q prime at lambda 1, phi 1, Q prime at lambda 2, phi 2. But if we use the usual rule, the Reynolds decomposition, which is what this is, Reynolds decomposition, of saying that by definition, the zonal average of Q prime is equal to 0. Right, so we're separating our flow into a mean flow, a zonal mean, and a fluctuation about that zonal mean, which by definition has 0 zonal mean. And then there's a couple other properties that are convenient to use. For example, Q times Q prime zonal mean would be the same as Q prime zonal mean, because if we make that decomposition, we have the average of Q, but Q bar in here, but Q bar has already been averaged, so Q double average is just equal to Q single average. We've done a zonal mean. If we average it again, we don't gain anything more. Okay, so over here we have this relationship between the second moment at these different field positions, the product of two first moments, and then this object. And this object is the second cumulant. So the third cumulant would be Q prime, Q prime, Q prime at three different locations. And we're going to ignore its contribution. Actually, it's not 0, but we're going to just decouple it from this equation here. We'll just drop its contribution. So this is really all predicated on the wave mean flow kind of ideas. We're basically doing a perturbative expansion, assuming that there's some significant mean flow and that we can perturb in fluctuations about this. This would fail if we were studying isotropic homogeneous turbulence. This has been known for a long time. But fortunately, nature is often kinder to us than isotropic homogeneous turbulence. We have macro turbulence, which it's characterized by typically zonal means and coherent structures, and it's usually anisotropic and inhomogeneous. Anisotropic and heterogeneous flows. So such flows give us some starting point at which to do a perturbative expansion. And I would argue that the physics of pure isotropic homogeneous turbulence is one of the hardest possible problems, and that it has stymied progress in the field by all the effort that has gone into that. Instead of thinking about perhaps some more geophysically or astrophysically relevant problems like this. So that if we give up some of the symmetry in our problem by not insisting on homogeneity and isotropy, allow the flow to be different in different points in space, and to have some non-trivial direction in which it's moving, like a jet, then even though technically it may be more difficult to make progress, you have a higher dimensional objects, we may have a good basis for a perturbative expansion. So that's what I want to argue is at least sometimes the case. Yep. No, because the second moment is non-zero. So we're going to allow this to be non-zero, and this is going to be non-zero. So the second moment is going to be non-zero. And actually the third moment will be non-zero. All of the moments in general will be non-zero, but the cumulants will vanish, or at least we'll pretend they vanish for third or higher. Okay, so that's a reason for looking at accumulants instead of moments. Moments, if you think about the moments of, say, a Gaussian distribution, it's going to have nth order moments, even moments, will be non-zero, never terminates. But for a Gaussian distribution, then only the first two cumulants are non-zero, and so you can stop there. Yep. Say that again, please. Oh, yes. So we know that for homogeneous isotropic turbulence, you have a cascade of energy. Say in 3 dimensions, you have a forward cascade to smaller and smaller scales. And so it turns out that this kind of approximation is equivalent to the quasi-linear approximation. So maybe let me talk about that for a moment. And in fact, this closure at this second order is an exact closure for the quasi-linear approximation, if you know what that is. So let me give this closure a name. We like to call it CE2 for a second order cumulant expansion closure. But it's also goes by the name of stochastic structural stability theory that Farrell and Ionu coined for essentially the same approach. And so dropping this kind of term here, we can think of this nonlinearity in terms of a wave picture. So we can consider this fluctuation as having some non-zero zonal wave number, and the mean flow has 0 zonal wave number. Now, if we do a Fourier or a decomposition in terms of spherical harmonics, this would look at like something like sum over L going from 0 to infinity, and a sum over M going from minus L to L of QLM times YLM of theta, phi, and lambda. All right, and so our zonal mean is all composed in the m equals 0 part. That's the part that has, so this oscillates like e to the I m times lambda, and so the m equals 0 part is zonally symmetric, and the non-zero m terms are ones that are oscillating as you go around lines of constant latitude. So this type of interaction here can be thought of in terms of what are called triad diagrams that were introduced, I guess, originally by Krejcinen. And the basic idea is that we would have a wave of wave number m1 and a wave number m2 come together and give us a third wave of wave number m1 plus m2. And this model, this Jacobian, respects wave number. And so these waves are interacting non-linearly, but they conserve their zonal wave number. So that's the general interaction. But when we throw out this kind of term here, then we've thrown out a lot of the types of diagrams that are important, and we've retained only two special types of diagrams. And one of those diagrams has wave number m and minus m combining to give us m equals 0, or the mean flow. So this represents two eddies of equal but opposite wave number coming together and driving the mean flow. This is the Reynolds forcing of the mean flow. The other diagram would have the scattering of a wave number m off of the mean flow. So not changing its m value because the mean flow doesn't have any m value. So this is the eddy, the interaction of the eddies with the mean flow. And this quasi-linear approximation has a long history, going back into at least the early 60s, if not before. But the realization that there was this exact closure for it, and to make use of this exact closure, has only come recently. So we don't have to do a quasi-linear simulation. We can just directly simulate these statistics and rely on the body of knowledge that's been developed for this quasi-linear system of equations. Yeah, the second one or both? So this represents an eddy scattering off of a mean flow. So imagine you have a jet that's going around the globe. And so that represents a strong mean flow. And now an eddy could come and interact with that jet and bounce off of it, but it's going to have to maintain its zonal wave number because the eddy, because the zonal flow itself is symmetric. Yeah. All right. So let me just give you a flavor for a little bit more detail of these equations, and then we'll look at the simulation, and then I'll just make some final comments because it's getting late. So we had this equation, which I'm just erasing, I see, for the mean flow. But let me write it down in a little bit more detail for you. Now let's be specific about our variables that we're interested in. So we're interested in the mean vorticity. So I'll call that the first cumulant, C1. We know that's only going to depend on the latitude, but I'll just write it in this more general way for right now. And it's going to be convenient for us to introduce something I'll call P1, which is just going to be the zonal average of the associated stream function. It doesn't have any more information in it because if we take the Laplacian of P1, we get C1. But it's going to allow me to write down the equations in a convenient way. And then we have C2 of R1 and R2, which is equal to the zonal average of the fluctuations, the eddies of omega of R2, R1. And we have, we'll call this P2 of R1, R2. Is equal to the zonal average of omega of R1 and psi of R2. And put a prime on those because we're dealing with the cumulants and not the means. We need that because the Jacobian involved both omega and psi. And we want to take the average of this equation. So we're going to have the we need basically the cross correlation between omega and the stream function. But again, this doesn't have any more information than this does, because we just take the Laplacian with respect to the second variable, and we get this because the Laplacian of the stream function is equal to the vorticity. All right, so then let's just focus on the equation for the time evolution of the zonal mean. So that involves j of omega and psi, as I mentioned. There's also the Coriolis term, but let me just focus on this particular term. And we want to average it. But we notice that omega and psi are in two different slots. We have to take a derivative like d by dx here and d by dy here. We want to glue these two things together in order to relate it to our correlation, or our second cumulants. So there's an easy trick to doing that, and we can just write that, use the fact that psi of R2 is equal to a, actually psi of R1 is equal to an integral d2 R2 of a Dirac delta function, R1 minus R2, times psi of R2. Right, that's basically the definition of a Dirac delta function. You integrate any function over with a multiplied by a Dirac delta function, it gives you the value of that function at the point where the argument, where R1 equals R2. So that just returns psi of R1. So we can insert that into our equation here, and then that allows us to have our two fields that we can take derivatives of. So this whole thing is going to be an integral dr2 of j of psi of R1 times j of omega of R1 psi of R2, and then we have the delta function. And now we can average this thing. And this is just what we call P2. So we've closed our system of equations. We have an expression for the tendency of the first cumulant in terms of the second cumulant. And then there's a similar equation for the second cumulant that involves the first cumulant and the second cumulant and the third cumulant, but we're dropping that third cumulant. Okay, so let's see how well this actually works. So let's lower down the screen. Yes. Yes, there's still the linear term, and so in the forcing in general, so I've only focused on the quadratic term because that's the source of the difficulties. So if you go to that paper on the archive, you'll see this in all detail. So I want to emphasize that I'm illustrating for this particular model, but I think that these techniques could be of interest in many other problems. And for instance, we've been looking at them applied to the ocean boundary layer, looking at convection and convective cooling of the top layer of the ocean causing convection, and then trying to treat the flows that result in this type of approximation, with the goal of trying to develop a subgrid model for the ocean, the mixed layer. Okay, so I'm going to run a simulation here. This uses a program that I've written called GCM. It's kind of an aspirational title. So the most complicated model it has in it is a two-layer primitive equation model, which is, I guess, beginning to be like a GCM. But so it's limited in capability, but on the other hand, you can download it for free from the Mac App Store if you'd like to run it. And there's a lot of different models you can choose from. I'm about to add a shallow water model. There's also a model of the tachocline inside a star, and various other things. We have the Antoine model, which is something we've been working on recently. But we'll do the stochastic model right now. So this is going to be on our rotating sphere, and it's going to have some stochastic forcing. And this program can integrate the equations. It can do both direct numerical simulation and then different flavors for direct statistical simulation. But I'm only going to show you the simplest one, the one that I just discussed. And it works in both spectral space and real space. And so I'm going to do this on real space. So the first thing it does is it builds up a spherical geodesic grid. And we're using a pretty modest resolution here of about 10,000 cells because this particular problem doesn't need more than that. So what we're seeing in the color field right now is the vorticity pattern. And let me just run it for a moment. The stochastic forcing is acting right now. And I've chosen for this numerical experiment a particular choice for this stochastic forcing, which if we look at this on a cylindrical projection, you'll see that most of the forcing is confined or is located at lower latitudes. I've basically chosen the spectral distribution of this forcing such that it's concentrated at these lower latitudes. And in fact, if we look at the power spectrum here, then we'll see that this is in spherical harmonic space. So this is the spherical wave number. This is the zonal wave number. I'm just populating these modes up here, and I'm not allowing M to extend all the way down to 0, which we would need to do if we had isotropic forcing. Okay, so the reason that we're doing this will become evident shortly. So let's go back and look at this flow and let it evolve for a bit. So the first thing you notice is basically just a linear model. So it's like one of Hinck's linear models for each of the different modes. But already the energy is beginning to grow in the system, and it's beginning to become nonlinear. And we're starting to see some tilting of these lines of vorticity and some structure beginning to develop. So we'll let this spin up for a bit. And already you're beginning to see some zonal flow develop, which I'll highlight by looking at the zonal velocity. So there are two jets right now. So there's the yellow color means it's positive zonal velocity, so it's blowing from west to east. And if we sprinkle down some particles, we can convince ourselves that it's actually being advected in this way. Now, the energy is going to continue to grow because the time scale for that damping is it's like, I think I've set it to be 50 days. So by the time about 50 days have elapsed, then things will come into a statistical steady state. Let's get rid of these particles for the time being. And what's going to happen is the kinetic energy is growing. We can see that down here where it's being tabulated. And then eventually it will plateau. And as the kinetic energy grows, then a length scale that perhaps Ted will talk about, the Rhine scale, is getting larger. And what's happening is it's going to squeeze those jets together so that only one prograde jet will appear on this planet. So this planet's going to actually have, this model planet's going to have super rotation. The jet along the equator is going to be moving in the direction of the planetary rotation. I think that's a consequence of my particular choice for this forcing, which was concentrated near the equator. And so different choices that stochastic forcing would lead to retrograde jets. So maybe there's something important in this, maybe not. Now you can see that the jet has merged together. And if we look at the development of this velocity over time, this is a Hofmüller diagram. And here's the start of our simulation where we spun up, and then the two jets formed, and now they're coming together, and it's becoming coherent. So let's do some time averaging now. And so this is our traditional mode for accumulating statistics in say a climate model. So at this, where that black line is, I've started turning on time average. This is also a zonal average that we're seeing. We're seeing the zonally average zonal velocity. And now we could look at, well, let me draw your attention to something here, which is that even though I was forcing this model only at the lower latitudes, there is flow all the way up towards the poles. So there have been eddies that are transporting angular momentum up to the poles in this full model. This is kind of our truth. This is no approximation apart from this, the approximations of the model itself and the spectral truncation, which is adequate here, or the spatial truncation. So that's our zonal mean, but we could also look at the correlations in our vorticity. Let's look at the second cumulant. So here's our flow of the vorticity. If I click here, this tells me what the correlation of the vorticity is at that point where I clicked and everywhere else on this sphere. And you can see that it's strongly correlated with itself, which it must be. And then there's anti-correlation some distance away, but it decays away from that point. All right, and so this is translationally invariant. This is testing basically this idea here that this correlation only depends on the difference in the longitudes. But if we go up in latitude, then the correlations look rather different. In particular, if we're up near one of the poles, then the eddies are weaker up there and the correlations are weaker. All right, so now let's repeat this by doing the second order cumulant expansion. So we'll go up to our methods of solution and choose the second order one. I'll do a fast integration. They're using the fact that these equations are stiff and we can use a semi-implicit integration. You can see that there are some more sophisticated versions that don't make some of the assumptions that we've made in dropping the third cumulant, and we'll see why those might be necessary sometimes. So we'll start over, and now the sphere, we're going to actually solve these equations in the space of spherical harmonics. The sphere that I built up was just for visualization, and let's look at the velocity field. So now I'm going to integrate the equation of motion for the first and the second cumulant. And what we'll see displayed here right now is just the first cumulant. And I'm only going to show you the zonal velocity, which we can extract from that first cumulant for the vorticity. So there's our zonal jet. And we've gone to this fixed point. You can see how much more quickly this worked than the direct numerical simulation. So that's nice. But if we look at it a little bit more detail, we'll see that there's some deficiencies. So the flow up at the high latitudes is much diminished compared to what we had before. And that's because we threw out the term that scatters one eddy with another eddy. It gives us a third eddy. And that's the term that would be transporting angular momentum up to the higher latitudes. So although that's in one sense a defect, it's an illustration of how we can gain some understanding of this model by playing this kind of game, looking directly at the statistics and looking at the effect of this quasi-linear approximation. So we have some understanding of the role of the eddy-eddy interaction, and we also see that the speed of this calculation was much faster than the earlier calculation. So we have the benefit of both of these aspects that I mentioned at the start. We can look at the two-point correlation function, and so that was what we looked at before. And now we'll see that it's longer range than it was before. That you might expect the two-point correlation function to show more damage from this truncation of the cumulant expansion by throwing out the third cumulant, because that coupled back in directly into this guy. And it has more of a wave-like character because typically the waves are overemphasized in this approximation, again because we've thrown out the eddy to eddy interaction, right? So we can do much better than this, and there's a number of different approximations that we've developed over the past few years that address these kind of limitations. Based on going to retaining the third cumulant, or changing the rules of the game a little bit to either do an ensemble average, or we could redefine what we mean by a quasi-linear approximation and allow some long wavelength zonal modes to be included along with the zonal mean. This is something we call the generalized quasi-linear approximation. Yeah. Yes. So I have a point here, and if I move this point, the pattern moves. Yep, it just shifts with it. So it respects this fact that this is a three-dimensional object, so I can't visualize it conveniently on a two-dimensional plot. So instead, I pin one of the points and look at the correlations with respect to that. Yep. Okay, so I'm just about done. Let me just say that I mentioned some open questions. Let me just repeat a couple of them. So one is to learn how to speed up these calculations for practical purposes. So for instance, if we want to have a new model of the subgrid scale processes, can we use this kind of cumulant expansion to do this in a systematic way? If we're trying to model the atmospheric boundary layer, then we have to deal with condensation in the low clouds at the top of the boundary layer. How would we deal with latent heat in that nonlinearity? Antoine and I have been working a lot on equatorial waves and have discovered an understanding of why they can be very robust against scattering. So it might be interesting to explore the role of equatorial waves in the context of these kinds of statistical theories. And I think Antoine is going to tell you about this work that we've done, not on the statistical approach, but rethinking the origin of equatorial waves. Okay, I think that's enough. Thank you. Right. Well, so it's true that the macro turbulence has a wave-like character, and we're kind of exploiting that so that we can use a rather modest spectral truncation here. But from our experience looking at the ocean boundary layer, there are some pleasing features about that problem too. For example, we might be able to get away with assuming that we have homogeneity in the two horizontal directions. Certainly things depend on depth, but if we're looking at a small patch of the ocean, we could average over both x and y, and that would mean that our variables would have the same dimensionality. Our second cumulant would have the same dimensionality as the underlying fields. They'd both be three-dimensional. So that's lead to a drastic savings in computation. One might still have a lot of modes, and we've been using Fourier and Chebyshev polynomials to the sort of traditional basis for looking at that, but we've also been investigating whether we can do a further dimensional reduction using proper orthogonal decompositions, basically techniques to find the most important modes. And so that seems to show some promise. Yep.
What's the statistical explanation why the CE2 does not capture the initial transient feature for the two merging?
Oh, it can. So let's look at the timeline here. So, well, okay. It depends on the initial condition. So I gave it a strong. So we played with this. We'd be able to see this. So I didn't tell you what my initial condition was for the second cumulant, which is I assumed that it's delta correlated in space. It's kind of a maximum ignorance idea. We know that it must be positively correlated with itself. And I gave it a rather strong kick to start off with. If we'd done something a little bit more realistic, then we would have seen actually these two jets merge into one. Yeah, that's been investigated by actually Farrell and Ayanu have looked at that. Yeah.
So all this one physically understand the long range correlation. So you mentioned that's because you're throwing away the 80 terms.
Right. So there's always the correlations are always going to have some long range character, but they just happen to be longer ranged in this approximation because we've eliminated important scattering processes. So the scattering of a wave off of the mean flow doesn't change its wave number, so it keeps it very coherent, too coherent. And if we looked at this in spectral space, let's take a look at that. Then we see that there's a lot of blank, a lot of white here where there's no power. And that's related to this idea that there's not this cascade anymore because we've thrown away these eddy scattering processes. So this was the stochastic forcing, and these are the zonal means down here at m equals 0. Interestingly, a secondary instability develops in this system. Because the mean flow is strong enough, actually some new Rossby waves start to get excited. And so, so that's a mechanism that can generate some power in here. But a lot of the focus of these more sophisticated approaches we've been taking is to try to fill in this and give us a more realistic spectrum.
So the correlations you're seeing are essentially coming from the forcing?
Correlations are largely from the forcing. Yeah, in this case, they're largely reflecting the forcing. There's some from these wave numbers 4 and 5. Yeah.
Just a technical question. So is it easy to run this model on Unix system?
Yeah. So this particular code, it's written in Objective C++ and Swift. The model part can be detached from the visualization here, and so that part can run on a Linux system. But the visualization part, I'm making extensive use of Apple libraries, so you would have to rebuild that on a different system. So, yeah. If you include third cumulants, yes.
Until which cumulant do you get something that is
Yeah.
made out to the
Right. So when we include the third cumulant, if you look in this paper, we get things that are very close to the truth for this actual model. Those calculations are quite expensive computationally, much more expensive. And they also suffer a problem that I haven't discussed called realizability. They have some problems that we have to deal with technically to make sure the probability distribution is positive. And we found a couple ways to deal with that. So I don't think that's the route to go for more realistic models. It's just going to be too expensive. But there's a number of things that we found that are much less expensive that are able to get similar accuracy. So I think that the outlook is still promising.
Can thank Brad again.
Thank you.